Alright, hi year 12s, this is Mr. Lim here again, and this is our video on Friyays number 3, so let's get started. Okay, so this one here was answered only 63%, which was actually the lowest out of all of the questions, so this is the one that we need to make sure that we know a bit about. Okay, so acid-base indicators, what do we know about acid-base indicators? Okay, so they do change color as the concentration of hydrogen ion changes. That's why 1 was in all of them, so that's not really very helpful, right? But then let's have a look at all the others. Okay, so weak acids and bases. Okay, so the idea of that these indicators change color is based on the idea that they're going to change the concentration of hydrogen ions, and then because these indicators are weak acids and bases, that's why they'll interact with the hydrogen ions change in concentration. All right, so the idea is that if you've got a conjugate acid and you add more base to it, it'll consume that conjugate acid and change the color. All right, so I think that the videos show that I said that acid-base indicators are only or just weak acids, or they are weak acids. But if you think about it, all right, if you have a weak acid like, oops, that's too fat. If you have a weak acid such as CH3COOH, right, and we know that its conjugate base is CH3COO minus. Now, obviously, these aren't actually indicators. Or this thing isn't an indicator because we know that it's colorless, right? But if we have this system here, if we said that this one was red and this one was blue, right, the idea is that the indicator it will be like this substance when it changes color. All right, so if it changes color from red to blue, it means that this is an indicator, this is an indicator, this entire system is an indicator. All right, so that's the idea behind it's a weak acid or bases. All right, okay, the idea that it must not react with the reactants is not true, because the idea is that for the change in concentration of the hydrogen ions will affect the concentrations of the other things because they react with it. All right, and then they must be used in large volumes. That's not right, because you're only supposed to use a little bit of it because it's going to change the outcome of your titration. Okay, so it's only 1 and 2. This is the answer. All right, so that's that one. Next, look at the next one. All right, so 6 to 8, these questions here relate to this equation at equilibrium. So the equilibrium constant for this reaction at 298 K is 4 times 10 to the negative 24. Now, is that a very large or very small number? That's a very small number. Okay, so you should recognize that that's a small number, right? And what does that tell you about the information? Well, we should remember that the equilibrium constant is a ratio of products over reactants, or the concentration of products over the concentration of reactants. So a very small number means that there is a low amount of products and a high amount of reactants. Okay, so because there's a low amount of products and a high amount of reactants, let's have a look at what the things are. The pressure of the products is greater than the pressure of the reactants. Okay, well, that's not true, because there's going to be not much products and lots of reactants, so that's not going to be true. Okay, pressure of all species is going to be the same. Well, that's not true either, because because that's a small amount, we're not going to have lots of reactants, so the pressure of the reactants is going to be much greater than that of the products. Okay, so they're not going to be the same. And then pressures of sulfur oxides are greater than that of oxygen. Okay, that's not necessarily true. That's not presented in the equilibrium constant. Just because they have a coefficient here doesn't necessarily mean that those two are going to be greater than that of oxygen. And in fact, we should recognize, because that this is a small value, right? Because this is a small value, that means there's going to be lots of these, which means that the pressure exerted by the oxygen is going to be much larger than the pressure exerted by the SO3. Okay, so that's why that one is wrong. Okay, so especially that both sulfur oxides. So yes, the SO2 will probably be higher, but the SO3 will not. Okay, so let's have a look at the next one. Which of the following changes that will initially decrease the rate at which SO2 is consumed? Okay, so the key thing is here is that you're looking at the word rate. You always need to be looking at these equilibrium things saying, okay, what is it asking me? Rate or yield or something else? Okay, so which of the following changes will initially decrease the rate? So we're now thinking back to year 11. So decreasing the volume of the reaction vessel, that's not going to, because that's going to squeeze everything together and that's going to increase both rates reaction. Okay, decrease the partial pressure of O2. All right, so decreasing the partial pressure of O2, which means that you bring this O2 down, okay, is going to decrease the forward rate of reaction, right? And that's going to decrease the rate at which SO2 is consumed, right? So that's the good one. Whoops, that's not what I want. Where are you? Oops, that's not what I want. This is the one I want. Okay, heat the reaction vessel. That's not going to be good because you're going to go increase both rates of reaction, even though the forward is exothermic and you're going to favor the reverse endothermic. Doesn't matter because you're going to heat the reaction vessel. Both of them are going to go increase. Just one of them is going to increase more than the other. Okay, and then add an appropriate catalyst. Again, both of them are going to that's going to increase both rates of reaction. So this is not asking about which one is favored, right? This is just asking which one will decrease the forward rate of reaction. Okay, what will decrease the forward rate of reaction? Reducing O2. Okay, and then which one of the following changes will increase the yield? So now we look at the next idea, the yield of SO3. Okay, so not talking about the rate, but the yield. Okay, if you remove the O2 from the reaction vessel, it'll shift the reaction left. So the forward rate of reaction will go down, the reverse rate of reaction will stay the same. And so therefore it'll be a net reverse. And so therefore that's going to decrease the yield. So it's not that. Okay, so remember, when we do these things, you should be thinking, okay, what are the 5 steps? F, ROR, ROR, net, ROR. Okay, then the concentration of products, the concentration of reactants. Okay, so if you do this for each of these, you should be able to work out what's happened. So if you add an inert gas, that's not going to do anything because inert gases don't react with anything, and so therefore they are not going to change anything about the reaction. Okay, increase the volume of the reaction vessel. Okay, so let's have a look. If I increase the volume, I make it bigger, which means that I reduce the pressure of all. Okay, so I make it volume increase, pressure decrease, which means that the FROR will go down and the RROR will go down as well. The question is, which one is affected more? Is the reaction that makes less, which is the forward rate of reaction, right? So I have a net reverse rate of reaction, which means that the reactants are going to go up and the products are going to go down, okay? And that's not what I want. I want to increase the yield, so that's out. Decrease the temperature. So if I decrease the temperature, what's going to happen? If I decrease the temperature, the forward rate of reaction is going to go down, the reverse rate of reaction is going to go down, but which one's going to go down by more? It's going to be the endothermic, which happens to be the reverse. Okay, so therefore I have a net forward rate of reaction, therefore the products are going to go up and the reaction is going to go down, and that's what I want. I want the SO3 to go, I want the SO3 to go up, the products to go up. Okay, so that's why that one is the correct one there, right? But what is the point of this? Like, you know, you can't afford to forget all your equilibrium stuff going into semester 1 exam, semester 2 exam, so on and so forth. You've got to remember these steps here, and it just has to come naturally to be okay, let's go to that when there's an equilibrium question. Okay, and then finally, this one here, just testing your knowledge of what you remember about pH. You should remember that concentration of hydrogen ions is equal to 10 to the power of negative pH, right? This one here is one that's a bit tricky because this one is what happens if you forget that it's not 10, but you do 1 times 10 to the power of negative pH. And then the others with the 4, that's not relevant. Any pH with a round value like 3 or 4 will be 1 to the power of something, something, something. Okay. Also, just checking your ability to convert, because, you know, if you put this into your calculator, or if you put 10 to the power of negative 4, you might get like, 4 times 10 to the negative whatever, right? Or actually, sorry, 1 times 10 to the negative 4, right? And just making sure that you can count the number of jumps that you do to get the decimal place into the right place, all right? So that one was C. Yeah. Oops. C. Okay, so not that one there. That one was trying to be a bit tricky. Okay, so just making sure that you remember those. Next, okay, this one here, 74% of you got it right. The idea is that you would have to work out the products, whatever the products are at the equivalence point, that determines the appropriate indicator. So this one here, the products would be barium phosphate. Okay, what's barium phosphate? Ba3PO4 2. Okay, and the phosphate ions are basic. Okay, now you might ask, well, wait a minute, barium phosphate is actually insoluble, right? That's true. What will actually happen is that the phosphate ions, there is going to be, whilst it says it's insoluble, there's a very small amount that actually does dissolve. So there's just a very low concentration of barium and phosphate ions in solution. And then those PO4 that are in solution will be basic, right? So it is the phenolphthalein, and lots of you are like, how do I spell phenolphthalein, right? Phenol, PHTH, ALIEN, right? So phenol, and then alien, or just like alene. All right, so phenol, alene. That's exactly how you say it. All right, so then lastly, this one here. So I gave you this particular thing on each of your papers, but you can have a look at it here, right? Couple of key points. Number one, you've got to make sure that you're only picking the concordant results, okay? So lots of people were picking like all of them, and someone even just like took the final amounts and didn't work out the difference, okay? So you've got to look only at the concordant results, and there were only 3 concordant results. Okay, you have to show the average in the working space. You can't leave stuff out of the working space. And if you left stuff out of the working space, I did not give you a mark for it. So just remember, there's no point doing it on the table, writing it next to the table, and then using that value in your calculation without showing it somewhere in the working space. Okay, that's the first thing. Number 2, this idea of the wasmejiki, the water of crystallization in terms of the solid. Okay, so let's just go through this idea. What is water of crystallization? Water of crystallization is when there are water particles stuck within the ionic lattice when substances are a solid. Okay, so ionic lattice when it's a solid. Okay, as soon as you dissolve this, the ionic lattice breaks apart and now it goes all random. Okay, and what happens to those water particles? They float off. They float off because now they just join all the other water molecules that you use to dissolve that substance. Okay, so the idea then becomes, if it's in a solid form, like 12.211 grams of this stuff, you have to take into account the water, which means that you change the molar mass here for the for the hydrated compound, including the water. However, as soon as you dissolve it in the volumetric flask, it just becomes barium hydroxide, right? Or actually it becomes barium ions and hydroxide ions. But the idea is that their water is irrelevant. So when you do your equation, the water is not there, right? When you do any further things with it, the water is gone. So I like to show, even though this didn't get a mark, I like to show the idea that the number of moles of barium hydroxide in the volumetric flask is equal to the number of moles of barium hydroxide 3 water, because there's always a 1-to-1 ratio between this and this. Okay, there's a 1-to-1 ratio, and so therefore that's going to be the same value there, right? So as soon as the substances dissolve, the waters go away, but if it's in solid form, you have to take into account those waters, right? Especially with the mass and working out the number of moles present. Okay, this one here, right? This part here, this ratio, you've got to recognize when to use it. It's not always just like the bigger number over the smaller number. You've got to think about, am I going, this way going from a volumetric flask to an aliquot or a pipette, right? And therefore you go smaller, or am I going the other way? Am I going this way, going to be from a aliquot to a volumetric flask? Okay, because the direction that you go in determines whether you do 20 over 200 or 200 over 20. But you should always recognize that it is unknown, so what you're solving, so that's the 20 for the aliquot, over your known. Okay, right? Then balancing this equation, I had a chat about it in class, but the idea is that you need to practice these things and work on ratios of things. Okay, so if you see this, you see that barium is here, and this is the only place where barium is, there's 3 of them here and 1 of them there, you know that this coefficient has to be 3 times as much as this coefficient, right? This PO4, you can deal with polyatomic ions together. So this PO4, there's 2 of them here, there's only 1 of them here, so this coefficient is going to be double whatever this coefficient is, right? And then you should also recognize that the hydrogens here and the hydroxides here, they're now equal, they have 6 each, and one of those with one of those makes a water, so you need 6 of those, right? Can I say that lots of people forgot to put in this coefficient? So they were like, oh yeah, they balanced this, and then they didn't balance out the water. You don't write a full balanced equation, you don't get the mark. So wouldn't it be a waste of time that you've spent 5 minutes balancing this, and then you're like, oh, I don't need this water because I only need the ratio between these two? Well, wasted all that time for the mark that you should have got, right? So then you do the titer, aliquot, this was done fairly well, and then this one here, right? So you've got to remember that if you wrote this A, like up over the working area next to the thing and said, like, I saved it as A, doesn't matter. If it's not shown somewhere within the working area as this volume, right, as A, you can't use it there. This here shows that I used the concordant results, but I would even recommend showing that you picked out these 3 values and then divided by 3, so on and so forth, right? Yeah, so that was that. It was done fairly well. We'll have a longer chat about it in class. Adios.